welcome to CEC lectures. Myself Dr. Priti Jagwani from Department of Computer Science, Aryabat College, University of Delhi. So in the previous lecture under this series of artificial intelligence, we have looked into various script arithmetic problems along with their kind of solution strategy and the solutions also. Today's topic or today's lecture is dedicated to adversarial search and games. So, when we say games, there are so many competitive environments and we have seen computers playing chess or any other game for for that matter. There are competitive environments in which there are two or more agents and these agents have conflicting goal. In the sense, let us say if I am kind of playing a game with computer, then definitely I am an agent and also the computer is working as an agent, and we both have conflicting goals. In the sense, if I am going to win, then computer is going to lose. If computer is going to lose, if computer is going to win, I am going to lose. So, the agents have the conflicting goals, and these kind of conflicting goals in the case of games such as chess, maybe poker or Go, they are going to they give rise to adversarial search problems. And for so many AI researchers, the simplified nature of these games is actually a win-win situation, actually a plus point to Go, because the state of the game is actually easy to represent. I will show you how. And agents are usually restricted to some small number of actions whose effects are defined by precise rules. So, for playing the games, we have precise rules. So, action A is going to kind of going to affect the whole scenario like this. So, the effects are actually defined using the precise rules, and some games may have kind of a small number of actions. And the games which we which are commonly studied within AI, for example, we have chess and Go, are what we call, or the game theorists call these kind of games as deterministic. Why these are kind of why these are being called as deterministic? So, for example, chess and Go I was talking about, because there are kind of two players. Each one of them is going to take one turn after the other. Perfect information is also there, and these are zero sum games. So, the whole environment, if we talk about in terms of agents or in terms of piece, is what we call is actually kind of a deterministic environment, because number of players is known, whose turn is going to be the next, that is also known, whichever action is going to be performed by the agent, what kind of effect it is going to have on the whole game or on the whole scenario is having that perfect information. And also the kind of these are zero sum games. So, perfect information, when we say, it is also we can call the environment as fully observable. Also, when we say zero sum games means that it is good for one player, is just as bad for the other, and there is no win-win outcome. That means both cannot win. One will win, another will definitely lose. So, for games we often use the term move as a synonym for action, so whose term, and the position as a synonym for state. So, instead of state we call it as position, and instead of action we call it as a move or maybe apply. So, these kind of terminology is actually very common if we talk about if we are talking about the games. So, let us say the game is being kind of played between two players, and we are calling these two players, one is Max and another one is Min. Now, let us say Max is moving first, then the player takes turns moving until the game is over. So, Max moves first, then Min, and then Max, and so on and so forth till your game is over. At the end of the game, there are points to be awarded to the winning player, and definitely because one is winning, another one is losing, there are penalties which are to be given to the loser. And again, if we need to kind of define formally in terms of an, or from a point of view of an agent, this is going to be kind of, we can say, a combination of some points. So, the first dimension of definition of these games in a formal manner is S0, which is actually the initial state, which specifies how the game is set up at the start. So, for example, starting, this is the situation. So, this is the initial situation, this is S0. Then we have to move S. So, either 1 or 2, the player whose turn it is to move in the state S. So, state is S, and it's going to be the next turn is of either the player 1 or the player 2, or we can say the player max or the player min. Now, why are we calling them max and min? I will clarify in a short while. Then the next is the action, which we say the set of legal moves in the state S. So, for example, consider the scenario of a tic-tac-toe game in which you cannot put your cross on a place where already a mark by the opposite player, the mark of O is going to be is already there. So, that is not a legal move. So, actions is basically the set of legal moves in the state S. Then we have a result which says S comma A, which is the kind of transition model which defines the state resulting from taking that action A in the state S. So, this is kind of an kind of move. So, what is going to be the result if the action A has been taken and the current state is S. Then there is kind of the next thing, or the next dimension which we need to see is terminal and the state. So, a terminal test which says which is true when the game is over or false otherwise. That means, if the game is kind of we can say over, it is known as the terminal state, and from where we have started, that is known as the initial state, which is S0. And the states where the game has ended are called terminal states, and there can be so many terminal states in one particular game. So, we have seen that how are we going to define the game in from the perspective of an AI agent with the help of the dimensions initial state, to move, then there are actions, then there are results, is terminal test, and then finally the state. Within this line, we have one more dimension, we have one more point, which is utility. So, utility is actually defined on the basis of two parameters, one is S, another one is the P. And utility here is actually a function which we call simply a utility function. It is also called an objective, it is also called as an objective function or a payoff function, and this utility function defines the final numeric value which is given to a player P when the game ends in any of the terminal states. So, if any of the terminal state has been reached, the game is going to get over, then the utility function defines the numeric value which is kind of the objective function or of the payoff function, and that numeric value is kind of defining a particular player P. Now, consider the example of chess, where outcome could be either a win along with a loss obviously, or it could be draw. And let us say we kind of assign the values, win is being assigned as value 1, loss is being assigned as value 0, or we can say 1 divided by 2 to the power 2 in case of draw. Some games have a wider range of possible outcomes. So, for example, payoffs in the back game on range starts from 0 and it can go up to 192. But in case of chess, we do not have a much larger or wider range of the possible outcomes. So, possible outcomes can be a win-lose or it could be a draw. Now, when we were talking about the min and max, we are going to look these kinds of games in the form of a tree, which is more commonly known as game tree. And soon I am going to show a game tree for the tic-tac-toe games, which is we also call this noughts and crosses. And from the initial state, so for example, the max player is going to start with the first move. So now max has 9 possible moves, because there are 9 possible kind of, we can say, cells in which the max player can put his or her mark. Now there are kind of plies which go alternate between max and min, and alternate between max placing a cross and min's placing a kind of knot, until we are going to reach the leaf nodes corresponding to terminal state, such that one player has 3 squares in a row, or all these squares are filled. So if all the squares are filled and no player is having 3 squares in a row, that is actually a draw. And if one of the player has 3 squares in a row, we have kind of we can say win, and other one is losing. So min is placing a knot while max is placing a cross, and they are taking their moves in turn. Now number on each leaf node indicates the utility value of the terminal state from the point of view of max. If we say high values are obviously good for max but bad for min, and that is why these players are not being kind of named as A and B. They are being named as max and min, because high values are actually good for max and bad for min. So here is kind of, you can see that you can see a game tree which is representing the game noughts and crosses, tic-tac-toe more formally we can say. So the max, when it is going to take a turn at the start of the kind of tree, we can say, because max is going to take the turn, all the 9 possibilities are actually open for him. Now what are the 9 possibilities? Either kind of the first row first column, or first row second column, or first row third column, and all these kinds of things. So all the 9 possibilities of how this max can have their can have its turn is being represented in the second row of the tree. Coming on to the next one, which says min. Now it is the min turn. Now for example, min is going to take a turn taking from the first possibility where the max has already placed its cross in the first cell as in first row first column. Now if min is going to kind of proceed further with this kind of situation, what all possibilities min is having? So except that cell which is filled with cross, your min can have all other 8 possibilities open. So there can be different 8 possibilities arising from this particular situation. Then again the next ply or the next move or the next turn, we can say, is for this max player. Now max player, let us say is going to take the situation from where max has placed in the first row first column, min has placed in the first row second column. Now from there again max is having kind of 7 more possibilities. So this is actually going to be the situation, and at the end if you can see which are the terminal states. Now their terminal states are kind of we have -1, the utility can be calculated as -1, or in case of draw it can be calculated as 0, or it can be calculated as +1. So this is what actually your kind of a game tree is going to represent. So from the max point of view, if max is losing, it is going to be -1. If it is a draw, 0 for both, or if your kind of max is winning, then in that situation we will represent it as a +1. So at the terminal kind of row, you can see the 3 different outcomes. The middle one is the 0, which is a draw, and in the -1 you have that min 1 as the winner, while in the plus 1 it is having the max player as the winner. So, in this way we are going to represent the complete game tree, and hence we have given the names of the players as max and min. So, now max wants to find a sequence of actions leading to a win, but min has definitely some other plans about it. This means that the max strategy must be a conditional plan, which is kind of an contingent strategy specifying a response to each of min's possible move. In fact, for such games, the definition of winning strategy for the game is identical to the definition of a solution for a non-deterministic planning problem. In both the cases, in the case of a non-deterministic planning problem or in the case of these games, in both the cases the desirable outcome must be guaranteed no matter what the other side is going to kind of do, or what all actions the other side is going to perform. So, for games with multiple minimax search outcome scores, we need we can say a slightly more general algorithm, and that general algorithm we call as minimax search. Now, within this minimax search, the possible moves for max at the root node will be labeled as, let us say, A1, A2, A3. The possible replies to A1 for min can be B1, B2, B3 and so on and so forth. I am going to show this with the help of an example, with the help of a figure soon, and this particular game is going to end after one move each by max and min. So, this kind of a game tree, if you can see. So, here we have a max, and the arrow or the direction of the kind of triangle is actually representing is going the triangle is going in the upward direction, that means it is representing max, and at the min level the triangle is going in the downward direction, that means it is representing the min level. So, from A it can have A1, your max can choose A1, A2 or A3. Now, the min, in case of min, from the nodes B, C and D, it can move to either B1, B2, B3 or C1, C2, C3 or D1, D2, D3 for that matter. And every kind of we can say triangle or every move is labeled here with a score. So, for example, A is going to take max is going to take A1, and then your B is going to take, let us say, B1, then the final score will be 3. Now, in these kinds of minimax trees or in these kinds of games, we can say the ply word actually means that both the players have taken in action. So, the word ply is used to unambiguously mean one move by one player, bringing us one level deeper in this game tree. So, the max ply and then the min ply and then so on and so forth. And the utilities of the terminal state in this game they are actually, if you can see, they are ranging from starting from 2 to 14. Now, what actually we need to do? So, for example, if max wants to kind of maximizes its chances of winning. So, first of all, let us see start with the bottom up approach, B1, B2, B3. Now, what is the minimum, which is the minimum utility? So, minimum is 3 of these. So, B is being marked as 3. Then if we can look into C1, C2, C3, again we are looking for minimum. So, minimum of 2, 4, 6 is going to be 2, and simply kind of minimum of 14, 5 and 2 will be 2 again. So, this is kind of we can say one ply or one move. Now, at the level max, if we talk about, now we at the max level we want to maximize the utility values, and here the utility values to be chosen from is actually 3, 2 and 2. So, the maximum here is 3, and that is why the node A has been labeled as 3. So, basically starting from the bottom we will go to the top. looking into whether we are actually looking for the minimum at that particular level or we are looking for the maximum value at that particular level. The 4 nodes are actually max nodes, in which it is max turns to move, and the 5 nodes are actually the kind of min nodes. Terminal nodes are showing utility for the value, utility from the perspective of max, that we need to be kind of very careful, because utility values are for max, so that the other nodes can be labeled with their kind of minimax values. So, max best move at the root is A1 because it leads to the state with the highest minimax value, and the min's best reply is B1 because it leads to the state with the lowest minimax value. So, the lowest minimax value is B1. So, for the min player it is going to be the move B1, while from the perspective of the max player it should be kind of what we can see is the best move is going to be from the root is A1. So, in this way we are actually we can say going to look into these game tree. If we are given a game tree, the optimal strategy which we need to determine is can be done by working out minimax values, as I have just kind of shown in the just stated in the example of each state in the tree, which is kind of a minimax state. The minimax value is the utility for max from the perspective of max. Let us make it very crystal clear, of being in that state, assuming that both players play optimally from there to the end of games. Minimax value of a terminal state is nothing but just its utility. In a non-terminal state, max prefers to move to a state of maximum value when it is the max turn to move, while min obviously prefers to a state of a minimum value when it is kind of min's turn, that is minimum value for max and maximum value for min. So, if we want to kind of we need to look into these kind of minimax trees, or we need to kind of formalize them into form of a function, or which can be used in an algorithm of this minimax search, is this can be a function of 3 states. So, one is, so minimax of S can be kind of utility which is S comma max if S is the kind of terminal state. Then it could be maximum of all the actions, maximum kind of varied over all the actions, while minimax result of S comma A if the kind of to move, if the state is if the next move is from the max point of view, or it could be opposite, it is going to look into the min of the minimax result S comma A among all the actions if it is if the min is to be moved from S. So, in this way we can say our minimax function can be utilized, or can be written in the form of a mathematical function. The terminal nodes at the bottom level get their utility values from the game's utility function which we have just seen in the defining when we were defining different dimensions of formally representing a game. The first min node, which is labeled B here, has 3 successor states with 3 values, which are 3, 12 and 8. So, the minimax value is 3 because we are looking for minimum. Similarly, the other 2 min nodes will have minimax value as 2. The root node, which is the max node, its successor states have the minimax value 3, 2, 2. So, it has a minimax value of 3 because we know here it is focusing on the maximum value. Also identify the minimax decisions at the root. The action A1 is the optimal choice for max because it leads to the state with the highest minimax value. So, in this way we can actually look into these minimax trees or minimax exploration of these minimax trees as a search algorithm, which says it needs to find the best move for max by trying all the actions and choosing the one whose resulting state has the highest minimax value. Algorithm is definitely going to be a recursive algorithm that proceeds all the way down to the levels of the tree, and then it backs up to the minimax value through the tree as the recursion kind of unwinds. And this minimax algorithm is actually it performs complete depth first exploration of the game tree if the maximum depth of the tree is m, and at each point there are b legal moves, then the time complexity of the minimax algorithm will be order of b to the power m. Space complexity, if we talk about, will be order of b multiplied by m for an algorithm that generates all the actions at once, or we can say order m for an algorithm that generates the action one at a time. If we talk about the complexity which we see as b to the power m, the exponential complexity max minimax impractical for both complex games like chess, which is having a huge branching factor of about 35, and the average game is having a depth of about 80 plus. Now, it is not feasible to search for this much of possible combinations, which is not which is equivalent to 35 to the power 80, and that results into 10 to the power 123 states. Fine. So, if this much of branching factor and this much of depth is there, we cannot use minimax trees for these kind of search problems, but yes, still minimax serves as a basis for mathematical analysis of games, and by approximating the minimax analysis in various ways, more practical algorithms can be we can say derived. Now, in this particular lecture, we looked into the adversarial searches and games, and we also looked into the minimax algorithm, the game and the games which can be shown in the form of game trees. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next. Till then, take care. Goodbye.